Starting from, let's start again. Today we're gonna talk about an actual case study of a BLT design to apply what we have discussed in the last session, starting from statement of the problem or setting the objective till job planning. Our problem today is a highly productive oil producing well that suffer from a communication between tubing and annulus problem and become a high risk and must be shut in. Actually, in offshore platforms, a well that's capable to produce naturally and has a communication problem between tubing and the annulus must be secured and must be shut in till securing. This is a big problem because this results in a big oil loss. So how can we solve this problem? Communication means there is a path between tubing and annulus in the reverse direction. So flow can go from tubing to the annulus. In offshore gas lifted wells, the normal pathway of the flow is injection gas go in the annulus side, then go inside the tubing. But if flow can go in the reverse direction, this well can be a high risk well because there is no control in flow in the annulus side because there is no surface safety valve inside the annulus. So guess what can we do to solve this problem? Actually, it depends on the situation. In certain situation, we are certain that our well is problematic and we can solve the problem of the well rigorously, and we must go and pull the completion and change it. Like, for example, a problem in the backer unset, for example. Sometimes when we do cased hole logging, we found that our backer is unset due to downhole conditions, for example, or bumping job, for example. So at this situation, the communication problem must be solved by rig workover, and there is no other option. Another situation is when your completion is an old completion and susceptible to corrosion problems. So there may be some holes in your completion and there is no baseline MIT log. MIT means multi-finger caliber log or multi-finger tool, imaging tool, multi-finger imaging tool, sometimes called MFCL, multi-finger caliber log. At this situation, this is just a tool with multiple arms that run inside your completion. It's a mechanical tool. Identify the shape of your ID. So when you run with this tool, you can easily identify the positions of the holes in your completion. So sometimes it may help you to identify the condition of your completion and if it can be solvable or not. Sometimes the corrosion of your completion is severe and you must go also with workover to solve the communication problem. And in other situations, there is only one or two holes that can be solved by straddle system. For example, there are certain through tubing straddle systems that can isolate any possible hole inside your completion depending on the condition of the corrosion. Other cases, like you have new completion in your well and you make communication test and you found that you have a communication problem. So you are using a gas lift completion and this completion is brand new, but you have a communication problem. So it most probably a problem in a gas lift valve, and you have many gas lift valves, more than 10 gas lift valves. So some operators prefer to go and blindly change some gas lift valves that are prone to corrosion, for example, and so that are prone to problems in the check valve, not corrosion, sorry. Because check valves of the gas lift valve, any gas lift valve had check valve to prevent reverse flow. So this check valve is a weak point in the gas lift valve and may be susceptible to corrosion or something of failure, for example. So you can go and change this gas lift valve and you solve the communication problem. Some operators prefer to change the valve that can be expected to be the problematic valve, but other operators prefer to run with BLT to detect the exact positions of leak points, because blindly gas lift valve change depending on your experience with your well is a risky operation, because you may end up with changing many valves and not solving the problem at the end, in addition to the risk of the operation. So The direct to go option is running with a BLT job first to identify the exact positions of the leak, then go and directly change the leaky valves. So the plan now is to run with a BLT because our case is a new completion well with many gas lift valves that are prone to failure. So we must first identify the problematic valves, then change them directly. So the objective of our BLT is to identify the leaky points. So we must make a proper design for this BLT string. As we mentioned before, the design includes first selecting the components of the BLT string and the deployment method, and finally specifying the sequence of the operation. Now we have set the objective of our BLT. We must now gather all the data related to our well from the history, completion diagram, and tally. The history, of course, is very important because if your well is susceptible for scale problems, for example, this will affect your choice of deployment method. Also, completion diagram and tally is really important because it affects the size of your tool string and the components also of your tool string to ease the deployment of the tools. Deviation survey is very critical because it is the most important factor that will affect the choice of your deployment method. Downhole pressure and temperature will also affect the tool's selection because each tool has a limitation for pressure and temperature. PVD data is really important because you must know what fluids you will go and deal with. Well production data will give you a picture of what you will face in your well and what type of fluids you will face in your well. Also, presence of hydrogen sulfide and carbon dioxide is really important because this will affect the cable. If you will go with E-line, for example, there are certain cables for harsh environments that contains hydrogen sulfide or carbon dioxide. After gathering all the data, you are now have the objective of your BLT and all the data of your well. You can now easily design your BLT string and deployment method. From the data gathered, our well is less than 30-degree deviation, and we have a slickline unit on location, and offshore platforms sometimes are limited in space and capacity. So you can go with slickline, you can go with your BLT on a slickline, especially that you don't need well stability or real-time data. Slickline limitations are that you are logging on a memory mode, so you can't know what is the condition of your well while logging. So if this isn't an issue for you, you can go with slickline and log on a memory mode, no problem, because our objective is detecting only the leak. So detecting the leak don't need any stability for your well, so you can go easily on a slickline and no need for stability, no need for real-time data, and it's a good option, especially that you have slickline on location. And most of the time slickline equipment are lighter than E-line equipment. So our first selection is the deployment method, which is slickline on a memory mode. As we are looking for the leak points, so no need for any fluid identification tools. As mentioned before in the last session, one of the basic components of our BLT string is the fluid identification tools. Those tools will help you identify the type of fluids that you are producing. But in our case now, there is no need to know what's the type of leaky fluids. No, we need only to identify the leaky valves and then go and change them. So no need for fluid identification tools, or pressure, no need for pressure downhole or gamma ray. We need only a correlation log like CCL to identify the completion accessories, and temperature and continuous spinner to log inside the tubing to identify the exact positions of the leak. So our tool string will include only CCL for correlation, temperature, and spinner for leak identification. Also, the minimum restriction in our well is XN nipple 2.6 inch. So we can go easily with 11116 tools with 218 shroud continuous spinner. Of course, the bigger the spinner, the larger the OD of the spinner, the better the resolution of the spinner. So we always look for bigger or larger OD blade spinners. The pressure and temperature of our wells are normal, not high B, high T wells, so we can go with the normal tools. Most of our tools are limited to around 350 degrees Fahrenheit. So our well temperature is below this value, so we can go with the normal tools. But there are certain tools that can be run when the temperature is above 350, and those tools are for special purposes and can be run for a limited time. After selecting the basic components of the tool string and the deployment method, finally we must make a simulation run. This simulation run must be done to simulate your tension while running hole and ball out of hole, to confirm the doability of your job. And this is a basic part of the design. Finally, the BLT components from top to bottom will be cable head, weight bars, and knuckle joints, then battery, memory, CCL, temperature, and continuous spinner. You will notice that there is no centralizer. For example, as we mentioned before, that one of the deployment tools that we sometimes use in the BLT is the centralizers. But to be honest, centralizers are really important in certain situations when we run with float identification tools, because most float identification tools need centralization to get representative measurement of the average flow inside the well bore. But in our situation, we don't need we don't have float identification tools, and we only need to exactly identify the leak points. So no need for centralizers to make the tool string simple and to ease the running of the tool string. So now we set the objective of the BLT, which is identifying the leak points, and selected the tool strings and the deployment methods depending on the gathered data of our well and the available equipment and the condition of our well. And finally, we must put all this in a program or a job sequence. The final program of the BLT will include both the objective and the selected tool string and the deployment method and the detailed sequence of the operation. This is a really important part of the design because you are looking for a leak. So you must condition your well to be able to detect the leak points. So how can we do this in an offshore gas lifted well? One of the possible options, this is not only the option we can do, there are many options you can do depending on your well and the situation and the availability of the pumping equipment and something like that. But in our case, we have gas lift on location, so we can build up pressure using the high pressure gas source. So in order to force flow through the leak points, we make the following sequence. First, we build up pressure in both tubing and the annulus using the high pressure gas source. Then sometimes we can't go, so we can't run in hole with slick line equipment while the high pressure, while the wellhead pressure is high. And in this situation, we can go directly to step 3, not starting by step 1. But in our situation, we can do this. So we first build up pressure in both tubing and the annulus, then starting running hole with the BLT string inside the tubing, while slowly bleeding the pressure inside the annulus to the production system. This will, of course, force flow through the leak points. So keep running hole at a constant speed as possible, especially against the possible leak points while bleeding annulus pressure. After reaching the bottom of the well, you can repeat again, building up pressure inside annulus and the tubing, because the pressure inside the tubing may be dropped after bleeding the annulus side because of the communication problem. You repeat step 1 again and build up pressure inside the tubing and annulus again, then starting ball out of hole with your tool while bleeding off the annulus side slowly to the production system. in order to force flow again from the tubing to the annulus. So while logging with the temperature and spinner, you can detect any flow through the leak points. If your situation necessitates that you can't run with your wellhead pressure is high, you can start bleeding wellhead pressure, then run in hole. After reaching the bottom, build up pressure inside the tubing and the annulus and start pulling out of hole with your PLT and bleeding the annulus to the production system. After getting the data, unfortunately, the data from the spinner wasn't representative, and there was a mechanical problem in the spinner, and only the temperature data was available. Looking at the temperature data with the wellbore configuration, we can find an anomaly in the temperature log at the valve number 6. This anomaly means there was flow through this valve from tubing to the annulus side, which means that the check valve in this valve is was filled, and this valve must be changed to solve the communication problem. After performing this job, Slackline changed this valve and repeated the communication test, and the problem is now there is no problem, and there is no communication, and the problem is now solved. So you saved around $2 million the cost of rig walkover, and also save many time and cost due to changing many valves blindly without any reference log. So running with PLT helped you to quickly and exactly identify your leak points, run and change it, and resolve your well. So this is all for today. Thank you. And any questions? I'm ready.
Thank you so much, Engineer Ahmed. So if anyone has any question, please don't hesitate to ask. Okay, we have a question of if there is any other log to show the anomaly, not only the temperature. Is there any other log than the temperature log showing the anomaly?
Actually, you can run with spinner alone, spinner with temperature and noise log. There are many logs that can be run to identify the leak, but the most common way is to run with a temperature log, temperature with spinner. But recently, there is a triple combination between spinner, temperature, and noise log.
Okay, thank you. So is there any other question? Okay, we have a question from Muhammad Mansour. It seems it is the orifice valve, right? If it is right, may that is why FGS won't be reliable.
Sorry, I can't get what you mean.
Okay, if you can open the chat and see the questions.
Okay.
Okay, can you see them now?
Okay, so let's see. That is the obvious one, right? What's FGS?
So FGS is the flowing gradient survey.
Flowing gradient survey while the well is flowing. You mean flowing gradient survey while the well is flowing? Of course, the point of while the well is flowing, the flowing gradient survey will give you the actual or the exact injection point. So this isn't necessary that the actual injection point of gas lift is a communication point. The communication point may be different than the injection point. So you must go with a survey while the flow in the reverse direction from tubing to the annulus, not in the normal direction, because normally any gas lift valve can be an injection point. So the injection point may be different from the communication point.
Okay, we have a question about what is the type of the software that we can use in this situation?
Any BLT interpretation software. In our case, we qualitatively look at the temperature and the spinner logs and identify the leak points. So you just can plot your data in an Excel sheet and you can identify the leak points. No need for any software, because this isn't a full interpretation or quantitative interpretation. It's just a qualitative interpretation. But normally we use Emerald, Plato, TechLog, any BLT analysis software.
Okay, thank you so much, Engineer Maher. I want to send you in the chat a feedback form. Please everyone fill it so we can always fulfill your needs. Thank you so much for being with us today. And thank you again, Engineer Ahmed, for your time. And we'll see you in our next webinars. Thank you so much.
Okay, thank you.